Okay, good morning everybody. If it's okay with you, I would like to teach through today without a break and finish a bit earlier because I need to go somewhere and we need to be at have some sort of doctor appointment with somebody, and I need to be there at 1 o'clock. So I would like to finish probably 20 to 1 or maybe 25 to 1, if that's okay. So we will not have a break, I'm afraid. If you get really tired, let me know. We still have a break and then we just finish a bit early anyway. Okay, so yesterday, and to some extent also also last week, we were talking about the phase transformation in these titanium and zirconium alloys, and the fact that when you're at high temperature you have a beta phase, BCC, and at low temperature you get an alpha phase. And we were talking about, particularly in respect of titanium alloys, that you might have beta stabilizers, which means that you actually end up with some beta phase also at room temperature. And the important point was that one of the important points was that we get this kind of large beta grains. We have this Burgers relationship, which we discussed yesterday. And the Burgers relationship is important because it means even though we have very large beta grains here, we don't have many different many different alpha orientations than in that beta grain. So you can actually see here. Well, let's work it out. Maybe this purple grain here, I think, is somewhere around here. It's quite difficult to see actually when you just look at the alpha map, and you see different colors here, but. And you know, actually, because it's IPF color, it's quite hard to say how many orientations you really have. But you don't actually see that many colors within for a single beta, for a region where you know that it all comes from one single beta grain. You should not have more than 12 different colors, or you can't actually. Most of the time, you actually see less. And of course, you see less because. One thing I would like to always remember when you do microscopy, you look at a 2D slice through a 3D grain, right? You cannot see everything in a 2D slice. You're not looking at an entire grain. You're only looking at a slice of a grain. A lot of people don't realize that. A lot of material scientists forget about that. So it's very important. Actually, just sticking to that, how do you determine grain size? Yes, generally. Sorry?
Then you're in stuff.
Okay, so you take optical micrographs, you draw these lines, and then you essentially. Yeah. Yeah. Okay, and what do you get from that?
An approximation.
Are you sure?
Absolutely not.
A lot of people say that. Everybody says that. It's actually wrong. Statistically speaking, it's a bit of a distraction here. But again, I think there's certain things that you as a material scientist should actually know that. You know, a lot of people don't. A lot of material scientists don't know that. Where, you know, if you're right, you would assume that you always have to cut your grain in the middle, and you don't. No, of course not. Statistically speaking, you're most likely to cut it here. Of course, it's a distribution. So actually, in principle, if you want to have the grain size, you need to do a geometrical correction. And it's essentially the number you get from your analysis times square root 2. And I'm always amazed that even when you talk to people at Rolls-Royce and all these big companies, they have no clue about that. So they've never really thought about that. So here you are. So you know, when you're on your job, you can be a smart ass and say, "Hey, look here, have you thought about that?" Right. Shitty thing. Okay. So now all this phase transformation we've discussed so far is actually very much about, you know, cooling down the material slowly, and then you get this kind of diffusional controlled phase transformation, like in steel where you get a perlite. But now, also like in steel, things might be a bit different when you quench your material. And effectively what you can get in titanium or in zirconium is martensite. Well, it's called martensite. Is it really exactly the same? What is martensite in steel? What is it? Oversaturated carbon in
Ferrite or alpha.
So ferrite, is it really ferrite?
No, not ferrite, but it's alpha carbon.
Yeah, but what is different with it crystallographically?
The concentration of carbon is oversaturated.
Yes, but what does it do to the crystal structure?
Deflects.
Sorry?
Many defects.
It distorted.
Yes.
I think that's what you mean. Yeah, distorted. So in steel, when you get martensite, you should get a distorted lattice. So instead of BCC, you get actually BCT. So body center tetragonal. So it's distorted. Now this is not quite what you get here. And that's why it is different. I mean, we use the same terminology, but for instance, we don't really have carbon in titanium, right? I mean, a few ppm, but not like what you have in carbon steel. And so the reason why we call it martensite is because it's a diffusionless phase transformation, right? So like in steel, you're talking here about a diffusionless phase transformation. Giving up on that. And so we also, as a result, we get a very fine microstructure, as you can see here. In fact, on the left, this optical micrograph, you can't really, it's very hard to see the morphology because the microstructure is so fine, and we really struggle to resolve that in an optical microscope. Oh, have I asked you, so what is the resolution of an optical microscope? Half the wavelength of what? Half the wavelength of what?
1 micron.
But the wavelength of what?
Light.
Of light.
Yeah, not light. Maybe light from
No, it's not electrons, it's light.
Oh.
It's really it's an optical microscope, it's the optical light. Right? What is the wavelength of light, with the light we see?
400
Yeah, 700 nanometers. So yeah, so we often say, and it's probably better than we often say the limit of optical microscopy is around a micron. It might be a bit better. In principle, it should be a bit better, but you should also always consider that the optics are never perfect. So the lenses you use, there's some astigmatism. So 1 micron, maybe a bit better than a micron, is good. But you know, if somebody tells you they've studied something with an optical microscope and they found that the grain size is half a micron, you should be very suspicious. And so if we need to go to higher resolution, we use electron microscopy, because actually with the electron we can achieve much smaller wavelength. So we can improve the resolution. Anyway, so we can quench these materials. However, the thermal conductivity of titanium and zirconium is actually quite poor. So in order to achieve high cooling rates, you need to be able to extract the heat quickly. And you only can do that with material which has a high thermal conductivity. So aluminium is a very good example, very high thermal conductivity. If you drop that in water, it cools to room temperature just in an instant. Steel still has relatively good thermal conductivity, but not as good as aluminium. And so, of course, when you produce if you want to quench and temper steel, you can't do it on very large cross sections because you just don't achieve the high cooling rates in the middle. In titanium and zirconium, it's difficult because actually the thermal conductivity is so poor that in principle it's almost impossible to achieve a proper martensite. And it's not really used to improve or to refine microstructures. So as from steel, there's this idea of, or it's actually very heavily used, you quench and temper to refine your microstructure. This is not something we necessarily do in conventional titanium and zirconium alloys. Where you might see this kind of microstructure is in welds, because in welds you might achieve very high cooling rates because you have a very small hot region and you have a large heat sink, and so it's possible that you can get these kind of microstructures there. But otherwise, it's because of the diffusionless phase transformation. This is a TM image here. You can see you get very, very fine microstructures in the kind of nanostructured material. But as I say, it's difficult to achieve, and you don't get a heavily distorted crystal cell. So the strength here, or the increase of strength, comes from the grain refinement only. Whereas in steel, your quenched steel is very hard, not just because of the grain refinement, but also because of the distorted lattice. And you temper it afterwards in that case to actually recover some ductility. Okay, so it's important to be aware that there's diffusionless phase transformation and there's diffusion controlled phase transformation. And most of the time, almost all the time, we will see diffusion controlled phase transformation in these alloys. It might be different maybe for people who work on additive manufacturing of, for instance, titanium alloys, where you might also see some martensite. And I know some people here in this room will probably do this sort of thing during their PhD. So then moving on, titanium alloys, they're actually quite a lot of different types of titanium alloys. And so there's some sort of classification we can use. They are commercially pure titanium alloys. So these are, they're not perfectly pure. because perfectly pure titanium is very, very difficult to achieve and very, very expensive. So they're called commercially pure. So there are some impurities in there. And in fact, they actually do add a few elements there, which I think we'll discuss in the next few slides. And of course, they are at room temperature. They are in principle alpha titanium. They just alpha titanium, more or less. Then we have single alpha titanium alloys. They're actually not that common these days anymore. Then we have what we call near alpha titanium alloys. Now, usually you would first discuss two-phase titanium. I have done it in the order of increasing beta content, as you can see here. Near alpha titanium alloys are not that common, but they are used by the aerospace or the aero engine sector, and we will discuss that later. Two-phase alpha plus beta titanium alloys are very common, and these are, so there's the kind of titanium 6-4, 6 aluminum 4 vanadium is kind of the workhorse titanium alloy. And so here at room temperature, these alloys have some beta phase. It's not as you might think from the terminology, it's not 50% beta, 50% alpha at room temperature. It's actually only maybe 5 to 10, 15% of beta. So beta phase is actually the minority. And then you have near beta titanium alloys. Again, these are actually not very common alloys. They are very interesting in principle because they can be extremely strong. So they have a much higher volume fraction of beta phase. Still, actually interestingly, they don't necessarily have more than 50% beta, even though they're called near beta. But they are very, very strong, but they are very expensive to manufacture. But we will also discuss those alloys a bit. Okay, so commercially, let's start with the commercially pure titanium. Now titanium is not just used because of its relatively, well, it's the potential of having a relatively high strength together with low density material, but it's also used because titanium is actually very corrosion resistant, and in fact so is zirconium. So titanium is used by the chemical and petrochemical processing industry in some areas where they need very corrosion resistant material. Essentially, when stainless steel doesn't work anymore, they might start to use titanium. They don't use it, they only really use it when they have to, because titanium is more expensive than austenitic stainless steel. They might also use it in cases where they really have a problem with the weight. Because titanium is a very light material, they might consider titanium in some cases. So you might find it in piping, heat exchangers, pumps, valves. But note, heat exchangers is the issue there, which I mentioned earlier, that it actually doesn't have great thermal conductivity. So it might not actually be a very good material from an efficiency point of view. It has high formability and weldability. So because it's a relatively soft material, it's quite easy, well, it's relatively easy to form. Now, some people would not think that is the case, because there are quite a few people who think that metals with a hexagonal close-packed structure are inherently brittle, but it's actually not true. So they can be formed into sheet. So and this can be done at room temperature. So they have really quite good formability. So here you can see at least, so there are different grades of CP titanium. At least the grade 1 and grade 2 here, they can be actually cold rolled. You can see that depending on those grades, you have different oxygen content. please don't think you have to learn now what is great, what is the oxygen content of these different grades. Just remember that there are different CP titanium grades, and that maybe in principle they become stronger with increasing grade, and it might be worth remembering that essentially the strength comes from increasing oxygen content, right? Because oxygen is a solid solution strengthener and an alpha stabilizer, absolutely. But it's an interstitial element, so it strengthens the material, but also makes it more difficult to deform, and that's why, as you go to higher grade CP titanium, you might struggle to do cold rolling or cold forming. You have to go to elevated temperatures. And then there's some iron here, and this is not just and I should say maybe also oxygen. It's not just an impurity. So these elements are probably added to some extent. Now, iron is interesting. Iron. Do you know which phase iron stabilizes? Beta. So iron is a beta stabilizer. You can see here actually how the strength increases. So you can see that actually titanium grade 1 has a proof stress of only 170 megapascal. That's really low actually. But you can also see just by simply, largely down to the oxygen content, by essentially more or less doubling the oxygen content, more than doubles the proof stress of the material. Iron is a beta stabilizer, and in fact, again, something which is, I don't think, very widely known is the reason why this is done is that you will find, if you look very carefully in these in the higher grade titanium alloys, you will even maybe in the lower grade one, you will find tiny pockets of beta phase in there. And the reason why this is done is because titanium and zirconium are very prone to pick up hydrogen, and the hydrogen has at room temperature practically no solubility, and forms hydrides. And so what you and that might embrittle the material, or reduce the ductility. The hydrogen, however, likes to sit in the beta phase, and if it sits in the beta phase, it doesn't precipitate out. It stays in solution there. So by adding a little bit of iron and having a tiny amount of beta phase in there, the idea is that this beta phase can mop up the hydrogen in the material and make any kind of slight contamination of you get during processing, any kind of pickup of hydrogen, even the smallest amount, will not result in hydride formation. I mean, the hydrogen content is held at a very, very low level in these materials, but it's essentially a safety feature to have a tiny amount of beta phase in CP titanium. So then we have alpha titanium alloys. So you can see now here some of the alloy compositions, and what you can see is that for instance here they do have additions of aluminium now, and aluminium is a fairly effective solid solution strengthener in titanium. And that's why aluminium is so commonly found in titanium alloys. You can also see there is some vanadium here. So this is actually a beta stabilizer, but it's so little that it doesn't become a two-phase alloy. It's still classified as an alpha titanium alloy, because at room temperature you will have you might have a tiny amount of beta phase again just to mitigate any issues with hydrogen, but it's not really a two-phase titanium alloy. Here you have an interesting variant with ruthenium in it. I believe that's actually used by the oil and gas sector. I'm not quite sure, I can't remember now why, but there's something in terms of the environment where they might use this material that it's beneficial to have ruthenium in there. You have also here alloys with tin. So tin, if you remember, is a neutral element. So here you really only have alpha stabilizer and tin as a solid solution strengthener, which doesn't affect much the alpha beta transers. It's considered a neutral element, although it's probably it's slightly a slight alpha stabilizer. You can see the oxygen contents here. They're kept at relatively low levels, although they're actually not that low, and some iron actually, and again the iron is here to just have this kind of safety feature of a tiny amount of beta phase to mop up the hydrogen. And then you might have some other additions, but actually here are the additions, so it's a more accurate number. And you can see that it's something you might not be aware of when they talk about a titanium 5 aluminium 2.5 tin. You might think, okay, it's 5% aluminium, but you can see that very often it's a range in reality. So it's 4 to 6% aluminium. Although actually that change from 4 to 6% we now know has a massive effect on mechanical properties. Yes?
It's all in weight percent.
Yeah, they are all, sorry, it's all weight percent. Yeah, it doesn't say that, it's weight percent. Most of the time we talk in weight percent. When we talk about atom percent, we specify that. But you're quite right to ask that. But you can see, so they are, especially down here, they are significantly stronger than CP titanium. The formability is not as great as CP titanium, but they have good strength. They can have quite good toughness, and they also have actually quite good creep properties and are weldable. Why do you think they might have? Well, why do they might have better creep properties than a two-phase alpha plus beta titanium alloy?
Because the grains are bigger.
Yes, you could argue that you might, in a single-phase material you end up with larger grains than a two-phase material, which is true. But that's not the whole story.
Beta phase is pretty small and act like precipitate.
The beta phase is the beta phase is probably morphologically looks quite small, but that actually would mean there's something, but it's about the beta phase, of course. And we discussed that before. What is fundamentally different with the beta phase compared to the alpha phase? The crystal structure. What is different about the crystal structure? Okay, so which one is BCC? And what is fundamentally different between BCC and HCP? Sorry?
To do with the slip length available.
Not slip length.
Closely packed.
That's right. Closely packed and not closely packed. Remember when we discussed diffusion rates? So creep is very much a diffusion controlled process. So if you have a crystal structure which is closely packed and has low diffusion rate, you end up with better creep properties. And by having some noticeable amount of beta phase in the material, you might actually deteriorate the creep properties of such a material. And that's why creep properties are mentioned here, because you don't have, well, apart from a very, very tiny amount of beta phase to mop up nitrogen, you don't really have any beta phase here. And so that can be beneficial. Strengthening is done through thermomechanical processing.